In this video, we talk about the laws for natural growth and decay. This is all inspired by the exponential function, or even more so by the miracle of the exponential function. Do you remember? The miracle was that there is a function which is its own derivative. Right? We had the equation d by dt y of t equals y of t, where y of t is the exponential function. And now we would like to generalize this relationship just a little bit, and then this gives us the natural laws for growth and decay. So we study a proportionality now between y prime and y. So we no longer assume they are equal, but we do assume that they are proportional to each other. In words, this means the following. It means the growth of a population is proportional to the population size. This means biologically that if we double, for example, the population size, then we double the growth rate. The more individuals we have in a population, the faster the population can grow. This is certainly a very reasonable assumption if the population is not too large. If the population becomes larger, so that resources are limited or space is limited, then this proportionality would no longer hold. But if the conditions are perfect and the population can grow freely, then this proportionality is a very, very good assumption. So how do we express proportionalities? Well, we use a constant of proportionality, which I call k, and then we write y prime equals ky. And then we have two choices for k. K can be positive or negative. So if k is positive, we call it the law of natural growth, and if k is negative, it's natural decay. Again, look at the equation. We all know that if y prime is positive, a population growth. So if k is positive, the population growth. If y prime is negative, y decays over time. So if k is negative, then we have natural decay. So in this video, I give you an example of each. So I will use a population model for population growth, for k is positive, and I will use a model for radioactive decay for the case k is negative. Let's consider the function y of t equals y0 e to the kt, and I look at its derivative. Y prime of t is d by dt of y0 e to the kt. And then y0 is a constant. I can take it out of the derivative, so this is y0 of d by dt e to the kt. And now for this exponential, we have to use a chain rule where the outer function is the exponential function and the inner function is just k times t. So then we get, well, first of all y0, and then we get the derivative of the outer function, which is just the exponential e to the kt, times the inner derivative, and the derivative of k times t is just k. So we get this. Then I rearrange the terms. I write this as k y0 e to the kt, and then I notice that this term is in fact y of t. So then I see that the function which I gave you in the beginning satisfies y prime of t equals k times y of t. So which means this function y of t satisfies the law for natural growth. Now something very interesting happens. So we found a function which satisfies an equation which has a derivative and the normal function in it. And this is actually what is called a differential equation. So a differential equation is an equation which involves the derivative of a function, and then if we say solution, we mean a function that satisfies this equation. So exactly as we have seen here, so y prime equals ky is a differential equation. And now if we call it solution, we are not looking for a number, we are looking for a whole function that satisfies this differential equation. And here is our solution. A solution is a function that satisfies the differential equation. So that's all I will tell you about differential equations for now. We will do this much later in the course and study differential equations in a bit more detail. Here we are really focused on the natural law of growth or the natural law of decay. And the differential equation just arises as a tool to understand those laws. Coming back to the function y of t is y0 e to the kt, we have the following general result. The only solutions to the differential equation y prime is ky are those exponential functions. y of t is y0 e to the kt. Let's look at these solutions graphically. So here I plot 2. Y of t is 2, e to the t is on the left. Y of t is 100, e to the minus t is on the right. And now I'm interested in the significance of these numbers 2 and 100. So where do they appear in this graph? Let's look at y is equal to 0. So if we write down y is 0, then we have y0 times e to the 0, and e to the 0 is equal to 1. So then this is y0. Aha! So this coefficient y0 in the equations is the initial condition. So let's see in the graph where it is. On the left side we have the increasing exponential. The initial condition arises at t is equal to 0. And in this graph it is 100. It is sitting right on top of t is equal to 0. So this is called the initial condition, and it arises as a constant in the exponential law for growth or for decay. Let's look at a population model. So now I switch variables, not to confuse you, but for populations we really often use p to indicate population. So I'm looking at p prime equals kp, same equation as before, just using p instead of y. And then I divide this equation by p. So I get p prime divided by p is equal to k. And now this relation gives us a meaning of this k. This k now arises as the growth rate per population. It is growth rate per population. And it has two names which I used both in the literature, so I have to give them both. One is called the relative growth rate, and the other one is called the per capita growth rate. So in your mind it should be the growth rate per individuum. So that's the growth rate of one individual. Okay, let's do an example for natural growth in a bacterial population. So we assume we have a bacterial culture that grows with a constant relative growth rate k. The initial count was 400 cells, and after 2 hours we have 25,600 cells. The question is, derive a mathematical model which describes the population growth and what is the relative growth rate k. And of course we are looking for exponential growth or natural growth, so we're looking for p of t, which is p0 e to the kt, where k is the per capita growth rate or relative growth rate. So the information we have in our problem is that after 2 hours we have 25,600 cells. So this equals p0, which is 400, and then e to the k times t, where t is 2 hours, k times 2. And now we have a wonderful equation which we can solve for k. So then we divide by 400, we get 256 quarters equals e to the k times 2. Now 256 quarters is 64, and then I take the logarithm right away. So then I have log of 64 is k times 2. And so this is easily solved for k. K is 1/2 log 64. And now 1/2 log 64 is the same as log of root of 64. So this is log of 8. And then you can compute this. This is 2.07. So wonderful. Now we found our per capita growth rate k. And then we can put the model together. So then we have the model is p of t is 400, which was the initial condition, e to the 2.07 times t. And this describes the growth of our bacterial population. Let's look at the example of radioactive decay. We all have heard about radioactive decay, and here is the radioactive decay equation. It is about a radioactive mass, m of t, and it satisfies a differential equation, m prime is equal to minus alpha m, where alpha is called the decay rate. And this has exactly the proportionality form which we talked about in this video if we set k is equal to minus alpha. So then k would be the rate of proportionality. To indicate it is negative, I use a minus sign in front of the alpha. Which means we can use what we learned before, and we have a solution to this differential equation. mt is m0, the initial condition, e to the minus alpha t. Now in the context of radioactive decay, there's always a report about the half-life of a radioactive isotope, and so we would like to compute the half-life. How is the half-life related to this alpha in our equation? So half-life is the time, which I call maybe t1. so that the mass of the radioactive isotope is exactly half of what it was in the beginning. So it is a time where m at this time t1 is equal to m0 over 2. It's just half of the original mass. So let's try to compute this. So then we have m0 over 2, this is the new mass, is the initial mass of e to the minus alpha t1. Right, at time t1 we have exactly half the mass, so we use a solution from above and we sub in t1. And now it's just a matter of solving this equation using our logarithmic rules. First I cancel a factor of m0, so then I get 1/2 is e to the minus alpha times t1. And then I apply the natural logarithm, so then I have ln of 1/2 is ln of e to the minus alpha t1, which is of course minus alpha t1. So then ln of 1/2 is minus ln of 2, so I continue here on this side, then I get minus ln2 is minus alpha t1, so the minus signs cancel. And what was I interested? Oh yeah, I wanted to know what t1 is. So I solve this for t1. I find t1 is log 2 divided by alpha. So this gets a box. It's an important formula for the half-life. It relates the decay rate alpha to the time it takes so that the radioactive isotope has lost half of its mass. So T1 is log 2 divided by alpha. Let's use this in a very important example of carbon dating. Right? Carbon dating is used to identify ancient objects and see how old they are. So for example, here we have a papyrus in Egypt, and it has 74% of its carbon-14 content as compared to plants today. So plants constantly absorb carbon-14 into their metabolism. Only if they die, they stop absorbing the radioactive carbon, and then it decays, and this is an idea to estimate its age. So the half-life of radioactive carbon is 5,730 years. It's quite long. The papyrus has 74% of its carbon-14 contents. We would like to know how old it is. To do this, we would like to use our radioactive decay equation from before, and there we need this alpha. So the first thing we need is the decay rate alpha. But for alpha we have a relation. We know that the half-life is log 2 divided by alpha. So we solve this for alpha, then we know that the decay rate alpha is log 2 divided by the half-life. Now in our case we have numbers, so this is log 2 divided by 5,730 years. So if we compute this, we get a low number of 0.00012. And then secondly, we use the decay equation, which is m prime is equal to minus alpha m, with a solution m of t is equal to m0 e to the minus alpha t. So what is m0? Well, we don't know what m0 is. We don't know what was the original carbon content in this papyrus because we were not there when it was produced. We know that 74% of its value has survived. So now m of t is 0.74 times m0. So let's sub it into the solution. Then we get 0.74 m0 equals m0 e to the minus alpha t. So we can cancel m0 or divide both sides by m0, and we are in business. We can apply our natural logarithm to find t. So let's maybe first sub what alpha is. So then we have 0.74 equals e to the minus 0.00012 times t. So now we have an equation for t. Applying the natural logarithm, so we have ln 0.74 equals minus 0.00012 times t, where I used one of the logarithmic rules for the exponential. This gives us a t which is equal to log of 0.74 divided by minus 0.00012. And then we can compute this number, and this number is 2,509 years. This means that the material the papyrus was made from is 2,509 years old. So whatever is written on it must be even younger. So this is how carbon dating works. Let me summarize. We considered two laws, the law of natural growth and the law of natural decay. And they were defined through differential equations. So for the growth law, we used P for a population. P prime of t is k times P of t. And we had an initial condition, P at time 0 is P0. We found the solution, P of t is P naught e to the kt. For natural decay, we had a very similar equation, but we used a little bit different notation. So we had m prime of t as minus alpha m of t, and the initial condition m at time 0 is m naught, and the solution is m of t is m naught e to the minus alpha t. Oh, what's going on with Gerlo and Marlow?